Okay, now we're going to proceed and use the shallow water model to actually perform a tsunami simulation. But before we do that, let's go back to the source code because there's a couple of things that we need to edit. So let's go in the application directory. So now I've copied the shallow water cppdef file into a new cppdef file called tsunami cppdefs. And let's look at this file here. So in this case, I still define the shallow 2D because that's what I'm doing, but I'm also going to use another definition called tsunami. Now, in the model physics, I'm also going to activate the u and v advection terms. So these would be the advection of the u and v component of velocity in such a way that this is the full shallow water model. Because the one that we were using before for the linear waves, had this approximation in which the advection term, the nonlinear component of the shallow water equations, were neglected. But this time we're going to retain these. Now, furthermore, I'm going to make a tsunami simulation for the whole globe. And as such, I'm going to have to mask the land in the model grid. And so I'm going to activate this definition called masking, which basically tells the model that there are going to be some computational points that represent land. The rest here remains the same. But then here at the end, I'm going to add an if-def tsunami, meaning that if this definition tsunami is active, I'm also going to activate the east-west periodic boundary condition in that, if you have a world grid, in the longitude directions, the system is periodic. Okay, so with these definitions, I can proceed then to compile the model using the tsunami compile, and then I just okay, that's the first step. Now, how about the grid? Well, if we go again in our home directory, we go in ROM's examples, and in shallow 2D, I've decided to use a particular grid, which is the world grid, which you have in your default path. It's called grd equals rnt grid load of wrd. Okay, oops, sorry, I misspelled here something. Yes, this has to be this sign. Okay, and if we plot this, this is a very coarse grid, h comma grd. So I'm going to plot this grid. So this is a world grid, okay? So it's a very coarse. Unfortunately, the shallowest depth is not very shallow, it's over 200 meters, which means that when the waves will reach the coast, you won't see, a rise in sea level. But you can reperform, you can actually, recompute the topography of this grid and make it a little bit better, with shallowest topography along the coast to see the effect of to see how when the wave reaches the coast, the amplitude is going to grow. But this is just for fun, we're just going to use it anyway. And so this is the grid, and we're going to put in this initial condition, a big bump here, maybe off Sumatra, to simulate the Indian Ocean tsunami of a couple of years ago. Okay, so this is the grid. So um, if we go in the input directory, you'll find that there's in fact a tsunami-grid, which is this world grid. And we have to build the initial condition, and those are simply built by going in the MATLAB directory. And I created an example script which is called su create initial tsunami, which is very similar to what we've been doing so far, except that now it's just placing a big bump in the sea surface height at approximately location I equals 45 and j equals 43. Anyway, you can go through the script. It's basically a big bump off Sumatra. Okay, so once we do that, then we can plot. I've already performed the run. You can perform it yourself at this point. I'm going to plot this tsunami wave. So let's go here. Okay, so we're going to increase this so that we have a nice view of the globe. Okay, here we go, and then we're going to press return. And so we see the initial amplitude perturbation, and then you see the wave spreading. And you see that as it approaches here the Indian coast, you have first a low elevation, and then followed by a high elevation, which is typical of tsunami. You have the low sea level, so the sea level kind of goes away, the water goes away, and then you have the big wave reaching. And you can see that in certain location, the amplitude is increasing a little bit, at the coast. Although, as I said before, the topography at the coast is not very shallow, so you don't see this amplification effect as clearly. You can also see that the waves are spreading around the world ocean, and you can see here the crest also arriving in the Atlantic. And if you follow this simulation long enough, you'll see that these wave crests are going to reach even the east coast of the United States. And in general, you can see that after a while there's a lot of noise, and you know that this is part of the also the gravity wave bouncing back and forth, from the continents. You also note that when the waves reach the deep ocean, they propagate much faster, and in fact we're not resolving this very fast propagation very well, and that's because the depth of the ocean is much deeper. Okay, so the wave speed is a function of the depth of the ocean. In fact, is the square root of g times h, where h is the depth. So this is kind of a fun experiment to do. You can reperform this experiment by running maybe generating a grid that is a little bit better than this, maybe a little bit higher resolution. This is about 1 degree resolution, which is kind of coarse, and also by ensuring that the topography is a little bit more accurate than what I've done here in a very fast way. Okay, so this is just an example of how you could perform your own tsunami simulation.